Alright, welcome to Lecture 10 on Physical Properties. In this lecture, we're going to address these essential questions. How do different types of bonds explain the physical properties of substances? What are the melting point trends for a group or a period? We're going to first start out with melting point trends. In order to understand the melting point trends, we have to apply our knowledge of chemical bonding. We have to look at both the covalent bonding that's going on, the ionic bonding, the metallic bonding, as well as the intermolecular forces that we addressed in our last lecture of van der Waals forces, dipole-dipole, and hydrogen bonding. All of these factors are going to be significantly important on the overall trends of melting points. So first of all, we're going to look at the trends for group 1. So I'm going to write out a few things here. So for group 1, on the periodic table, which is the alkali metals, we find the following trend. If you look at lithium, sodium, potassium, rubidium, and cesium, alright, and the melting points of each one of these. So 454 for sodium is 371, 337 for potassium, rubidium is 312, and for cesium it's 302. So looking at these numbers, what do you notice about what happens to the melting point as we go down group 1? Well, you should realize that the melting point is decreasing going down group 1. So as far as melting point is concerned, as we go up from top to bottom, the melting point is increasing. Alright, the question is, why does the melting point decrease as we go down group 1? Well, let's take a look at the type of bonding that occurs in group 1. All of these are metals, so the bonding that will occur is metallic bonds. So lithium, sodium, potassium, rubidium, and cesium are all metallically bonded elements. That means that their electrons, their valence electrons, are going to be delocalized, and they're going to be wandering around, and we create these cation networks that are going to hold those valence electrons together. Well, if you remember, as we go down group 1, the size of the element is getting larger. Alright? Because the size of the element, these metals are getting larger as we go down, the attractive forces between the nucleus and the delocalized electrons are reduced. And since they're reduced in attraction, it becomes easier to melt as the nucleus becomes further away from those delocalized valence electrons. Alright? So that should explain the melting point trend for group 1. Alright, so now what we're going to do is look at the melting point trend for basically group 17. On the periodic table, which are the halogens. Now, if you remember that these halogens are all diatomic, so we're going to start with F2 and Cl2 and Br2 and I2 and As2, okay? And their corresponding melting points are 54, 172, 266, 387, and 575. All right. Now, if you compare these to group 1, there's a major difference here. Group 1 has much higher melting points than Group 17, but you got to remember that in Group 1 the melting points are determined because the bonding nature of Group 1 being metals, metallic bonding. So metallic bonding is very, very strong compared to the bonding that's occurring in Group 17. So the bonding in Group 17 are going to be dictated by van der Waals forces. These are all nonpolar elements, so fluorine, chlorine, bromine, iodine, acetine. So the bonding that's going to be really determining the melting point here for Group 17 is van der Waals forces. So looking at this, what's happening to the van der Waals forces? Well, as we can see, the melting point is increasing as we go down in Group 17. So what does that tell us about the van der Waals forces? Well, the van der Waals forces must also be increasing then as we go down. So the van der Waals. Right? Now, why are the van der Waals forces increasing? Well, it's due to the size of these atoms. All right? What we find is that the larger the atom, the stronger the van der Waals forces are. And so fluorine being the smallest is going to have the smaller van der Waals forces, where acetine down here at the bottom of the group is going to be the largest, so it's going to have the strongest van der Waals forces. So it's important to remember this, that the van der Waals forces increases with increasing size of atoms. Alright? And so since the van der Waals forces are the determining factor of the melting point for these, for this group, therefore going from top to bottom, we're going to increase in melting point. Alright? So that's very important that you understand that. Alright, so now that we got the trends going down for Group 1 and 17, let's look at the trends going across a period in the periodic table. So if you look at this graph that we have here on this page, you will notice that we'll start with period 2. This shows period 1, period 2, and period 3. And so we'll just kind of look at period 2 because that will give us a better indication of what's going on here. So period 2 is going to cover lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Alright? So those elements here that we have underlined. Now, if you notice here, we have the trend going from lithium to beryllium to boron, and then up to carbon. There's a increase in boiling point or melting point. So typically what we see here is, as we're going across the periodic table left to right, from lithium to carbon, we get an increase in the melting point. Now, why is this the case? Well, first of all, lithium and beryllium are both metals. Alright, so these two are both metals. So they're going to have metallic bonding that's occurring. And the metallic bonding is going to get stronger as we go from lithium to beryllium. And that is due because lithium is larger than beryllium. And just like we talked about before, the metallic bonding gets stronger with a smaller metal atom. Alright, like we talked with Group 1. So beryllium has a higher melting point than lithium. But then what about boron and carbon? Well, why are boron and carbon so large? Especially carbon. Carbon has a huge melting point, and it's a non-metal. And boron is a metalloid. So what's going on there? Well, it turns out that especially with carbon, that carbon, if you recall back, it forms giant molecules, or these covalent coordinated bonds. And because carbon and boron can form covalent coordinated bonds, they have extremely high melting points. The covalent coordinated bonding, or those giant molecules, that network is so strong that it is very hard to melt carbon compounds, such as diamonds and graphite. Alright? Alright, so then we see after we get from carbon, there's this major drop down with nitrogen, oxygen, fluorine, and neon. And neon being the easiest to melt. And so we start out with looking, there's an increase in melting point, and then all of a sudden there's this major drop. Well, why does that major drop occur? Well, it's because nitrogen, oxygen, fluorine, and neon, their melting points are determined by van der Waals forces, because they're nonmetals and they're nonpolar. So therefore, they're going to be determined, their melting point will be determined by the van der Waals forces, which are quite weak, quite weak compared to metallic bonding and those giant bonding molecules that are covalent coordinated. Alright? And so we'll see this trend throughout the periodic table. You'll also notice in group 2, erase this, in group 2, you see the similar trend. You see from sodium to magnesium and aluminum, they're fairly similar there. You see a increase in melting point, but then the huge spike up for silicon. And why silicon? Well, because silicon can form a covalent coordinated giant molecule again. And then you get the drop and you get the downward trend here because of the van der Waals forces going on. So the bottom line, as we're saying, is that when we're moving left to right across the periodic table, at first we see a general increase in melting point due to metallic bonding. And then we see a very large increase in melting point that is due to the molecules or the elements that can form covalent coordinated compounds, or these giant molecules. And then we see a very big decrease in melting point due to the nonmetals forming, due to the nonmetals governed by their van der Waals forces in the melting point trends. Okay? So think about these ideas about melting point. Very important that you understand. They will be covered heavily on the AP and IB exam, so study them well. Alright. So now what we're going to turn our attention to is boiling points. Boiling point trends. Here's some organic compounds, a list of them, from methane to decane. And if you look closely to the boiling point trends here, you will notice that the boiling point is increasing as we go down this group, alright? So we have to understand why the boiling point is increasing going from methane to decane here, alright? Well, if you look closely to the molecular formula, what do you notice about what's happening in this series? And by the way, this is a homologous series here. These are all alkanes, as you'll recognize. And so what's going on? Well, if you look closely, you can see that the number of carbons are increasing. So a lot of times students will think, okay, the more carbons a molecule has, that must mean they have a higher boiling point. Well, sort of true, but it's more to do with their size or molecular weight. Alright? Now, all of these alkanes are all non-polar. And so that's what let's make a note of that. These are all non-polar. And since they're all non-polar, what are the forces that are going to determine the boiling point here? Well, just what we found with other non-polar compounds, the melting points are determined by the intermolecular forces. The same thing that occurs here with these molecules. The boiling point is determined by the intermolecular forces. Well, since these are nonpolar compounds, what are the intermolecular forces that govern nonpolar compounds? And if you say van der Waals forces, you would be correct. So, what appears to be occurring here is that as the molecular size, so as the size of these molecules are increasing, so does the van der Waals forces. And indeed, that is the case. So, let's write in here van der Waals. Van der Waals. Okay? The van der Waals forces are increasing as the molecules get bigger. And this is very much the same thing that we saw with the melting point for group 17. Remember, group 17, the melting point trend, the melting points got bigger as you moved down group 17 because the size of those atoms were increasing. So van der Waals forces, the strength, really determines by the size. The larger these molecules are, the more mass they have, the stronger the van der Waals forces, the higher the boiling points and melting points. All right? That is a huge and important idea. All right? So keep that in mind as we talk about these boiling point trends. Alright, so now we're going to look at a different set of molecules and their boiling points. Alright, so this graph is really important, extremely important. Alright, and so what we're going to do is I want you to study this graph for a minute and notice especially the boiling point trend that we see occur with oxygen, sulfur, selenium, and tellurium. Now, that each one of these is part of a group. This is the oxygen group on the periodic table, which the oxygen group belongs to group 16. All right. So here we're looking at group 16. The next one, HF, HCl, HBr, and HI, all of those belong to group 17, or the halogens, okay? And so all of these have different groups that are associated with it. Here's group 15, and down here, this is group 14. Right? So what we're going to do is we're going to compare these molecules with their group number as we go down. Okay? And so I want to look at this trend a little bit more here. Let's look at group 16. That's the oxygen group. And what we notice is that we had, go back. We had water, H2O, and then there was a downward deal, it was a pretty sharp downward deal until we got to H2S, and then we started seeing an increase from H2S to H2SE, and then we started still seeing an increase to H2TE, right? And so the boiling point increases in this direction. Alright, so what's occurring here? Why do we see this boiling point occur? Okay, well, first of all, let's take a look from H2S to H2SE and H2TE. Alright, now here we see an increase from, let's change this color here so you can see this. So from here we're getting an increase in molecular weight. Right? The molecular weight's increasing, and we know that when we increase the molecular weight, the intermolecular forces are getting stronger. So here, this part of the trend should make sense, because sulfur here is smaller than selenium, and selenium is smaller than tellurium. So the molecular weight's increasing, therefore the intermolecular forces are increasing. Well, what are the types of intermolecular forces that occur here? Well, if you look closely, these are all polar molecules. And since they're all polar molecules, the governing factors here are going to be dipole-dipole. So we got dipole, dipole that's occurring. And so just like we saw with the van der Waals forces, as the molecular weight is increasing, the van der Waals forces are getting stronger. Well, the same thing with dipole-dipole. As the molecular weights increase for a polar molecule, the dipole-dipole gets stronger, and so the boiling point goes up. So what about water over here? Why does water have such a high boiling point? It's got the smallest size, the smaller molecular weight, but yet it has the highest boiling point. Well, what's occurring there? Well, water is still polar, but it has an extreme dipole. It forms hydrogen bonds. And hydrogen bonds are so super strong intermolecular forces that they are going to create extremely high boiling points, even though they have a small molecular weight. So what you can kind of think of is in this order as far as intermolecular forces is concerned. Hydrogen bond, being the strongest types of intermolecular forces, are going to typically have the highest boiling points. Then dipole-dipole, and then van der Waals forces. Alright? So you're going to have to be basically asked to compare, given different molecules, what relatively who has the highest boiling point and who has the lowest boiling point, and why that occurs. And we'll talk about that some more here as we show these trends. Alright, so let's go back up here, and we'll see with these other groups. Let's do HF, HCl, HBr, HI. Alright, now here HF is going to have the highest boiling point due to hydrogen bonding. Alright, because HF will hydrogen bond because it has fluorine in it. But Cl and Br and HI, these ones here, will not form hydrogen bonds. They are polar, so they're going to just be dipole-dipole. And as we saw before, HI is the largest in molecular weight and size, and therefore it's going to have the highest dipole-dipole. Therefore, HI would have the higher melting or boiling point. HBr would be next because it's bigger than HCl, and so it's going to have stronger dipole-dipole forces and be able to bond better. All right. Now the last one I want to look at is the trend down here at the bottom here. CH4 is going to be the lowest, and then SiH4, and then GE, and then 10 up here. Now this we see our typical increase due to the increase in molecular weight. These are all nonpolar, so all of these are nonpolar in group 14. All of them. So therefore, they're going to rely on van der Waals forces. The van der Waals forces increase as the molecular weight goes up, and so we simply see this trend. And then CH4, of course, will not hydrogen bond, so it's going to be down here at the low boiling point. Alright? So hopefully you kind of are starting to get this idea here. Alright, so let's take a look at some things. First of all, what we should understand at this point, that metallic bonding is going to produce very strong bonds. And so metallic bonds, metals, are going to have the highest melting and boiling points. Ionic bonding is next, and then followed by molecules. Molecules are going to have intermolecular forces that are going to be associated with how strong those basically the intermolecular force is going to dictate how high the melting and boiling point are. So let's take a look at a few situations. Let's say you have copper, sodium chloride, let's do water, let's do H2S, and then we'll do finally methane CH4. Okay, so we have all of these molecules. I put these in order of increasing or decreasing boiling point. So the boiling point should increase this way. Well, why does the boiling point increase? Well, first of all, this one is metallic bonding. So copper forming metallic bonds are going to have the highest melting point. Next is sodium chloride because it forms ionic bonds. And ionic bonding is going to be strong, but not quite as strong as metallic bonds. And then the last ones here are molecules. Remember, they all contain nonmetals, so they have covalent bonding. Now, yes, covalent bonds are the strongest overall, but covalent bonds are going to hold these atoms together so tightly, so really it's going to deal with the intermolecular forces between the molecules that is going to determine if these molecules boil or melt. Okay, and so water is going to have the highest boiling point among these molecules because of hydrogen bonding. Then we have H2S, and that's just going to be dipole-dipole because it's polar. And then finally methane is nonpolar, so it's going to be dictated by van der Waals forces. And so we kind of get this idea that the bond type in the intermolecular force is going to have the governing impact on the boiling and melting point. Alright? So keep that in mind as you study these trends. Alright, the last thing we're going to look at is solubility. I have a chart here that you need to kind of know and understand. But the overall, when we talk about solubility, we're really referring to a water as the solvent. So everything is going to be based on dissolving in water. Now, the rule that I want you to understand here, and I would write this down, is called the like dissolves like rule. Okay? Now the like dissolves like idea is that polar compounds will dissolve other polar compounds, and nonpolar compounds will dissolve all other nonpolar compounds. But polar and nonpolar compounds do not like each other and will not dissolve very easily with each other. Alright? So what we see here with the idea is that ionic compounds are going to be soluble in polar solvents, such as water. Water is a great example of a polar solvent. And so ionic compounds are typically soluble in water. Now the degree of solubility can change. Some are a lot more soluble in water than others, but still in general we say ionic compounds are soluble in water because they're extremely beyond the polar capacity. And so the like dissolve like rules applies there. Now polar compounds are soluble in polar compounds, but nonpolar compounds, they're not soluble. So in other words, this is why oil is a nonpolar compound. Oils will not dissolve in water. They don't mix because oil is nonpolar and water is polar. And so they simply just will not mix. Okay? But you flip this idea and you get a nonpolar solvent. Well, a nonpolar solvent could be like oil itself. Oil itself. And so polar or ionic compounds are not soluble. Polar compounds are not going to be soluble, but a nonpolar compound will be soluble in oil, such as methane, CH4. So CH4 will dissolve in oil because nonpolar will dissolve nonpolar, and polar will dissolve polar. But polar will not dissolve nonpolar, and nonpolar will not dissolve polar. Hopefully that makes sense. I know it's a little crazy. So think about that idea on solubility. But that's all I really want to say about solubility at this point. Alright? So there we go. We're done with this lecture. Make sure you study it really super well. It is a very important lecture to understand. We will discuss some points in this lecture in class, make some clarifications, but remember you will have a quiz on this lecture. Alright, so that is it for now.